I really sincerely think that we're choosing my talk. I'm really excited to tell you about some of the project I'm currently PhD. Before I tell you about the projective span, I want to tell you a bit about span, which is otherwise known as the vector field problem. So if you have a smooth manifold, a vector field on any smooth section of the tangent bundle, and if you have k vector fields, we say that they're linearly independent if they're pointwise linearly independent. The span of a manifold is defined to be the maximal number such that the manifold emits that many linearly independent vector fields. So in other words, the span of some manifold is at least k if and only if the tangent bundle admits a rank k trivial subbundle. So in my notation here, I'm just assuming that this is like a real manifold, but it doesn't have to be. The vector field problem has a really rich history. Probably the most famous span computation is the span of spheres. Hurwitz and Radon gave a lower bound for the span of spheres in the 1930s, I think. They were algebraists studying some kind of composition formulas for quadratic forms. So their proof was very, very elementary. Nowadays, their lower bound is created in a kind of slick way using Clifford algebras. But decades later, Adams famously showed that the lower bound was the same as the upper bound using K-theory and, of course, Adams operations. But that's kind of a cool example. I'm also trying to popularize this result. People don't seem to know this about Stiefel manifolds. But if K is equal to 1, the N1, which is the Stiefel manifold of 1 frames in Rn, that's just a sphere, a minus 1 dimensional sphere. So K is not 1, then the Stiefel manifold Vnk is actually parallelizable. So the tangent bundle is trivial. There's many proofs of this, but my favorite is this paper at Handel. It's a very short, explicit paper. I'm not really interested in vector fields, though. I'm interested more in line fields. So if you have a smooth manifold, a line field is now a smooth section of the projectivized tangent bundle. And if you have k line fields on M, we say that they're linearly independent if, for a point on the manifold, the k tangent lines at that point span a k-dimensional linear subspace of the tangent span. That point, that's what I mean by linearly independent. And just as before, projective span is the maximal number of linearly independent line fields on the manifolds. And just as before, projective span is at least k if and only if the tangent bundle admits a subbundle of k-line bundles, the direct sum of k-line bundles. We really have very few manifolds for which we know the projective span, at least in any interesting cases. It's not too hard to compute the projective span of surfaces and three-dimensional manifolds. This is just a simple example where the span is different from the projective span. The Klein bundle, its tangent bundle splits as a trivial line bundle and a non-trivial one. If you think of the Klein bundle as a circle bundle over a circle, you can realize it as an instance of something called a solved manifold, which is a homogeneous space of a connected solvable Lie group. These things, I don't really know much about them. I think they're a bit niche, but they apparently have come up in the study of dynamical systems. And I've come to learn that they also arise somewhat naturally in the study of discrete subgroups of Lie groups. So I think there's some kind of, geometry, algebra, number theory story showing all these solved manifolds. And there's this really striking Annals paper from long ago, where Alexander and Sharba show that these compact solved manifolds are line-element parallelizable. So the tangent bundle splits completely into lines. And I think that result was important to these areas that I mentioned. Another cool example that we sort of have some information about is the projective Stiefel manifold. So here you take a quotient of the Stiefel manifold where you identify a frame that's negative, basically. And it's known that this thing is stably line-element parallelizable. So if you take the tangent bundle and you add some number of trivial bundles, that resultant thing splits completely into lines. I have some dubious circumstantial evidence in the form of computer experiments that this thing is actually line element parallelizable, but I don't know how to prove that. I think it might be true, and this projective steeple thing is important. It was classically important because knowing its span and also pspan could have implications in something called the generalized vector field problem. Don't have time to tell you about that, but if you're interested, you can Google it. But also, it would have implications in the emergence of RPN, which is another interesting differential topology problem. So what I'm trying to get across here with this very short list of examples is that there's some cool manifolds lying around. They have uses in different interesting areas. And sometimes knowing about vector fields and line fields on these manifolds can be really powerful and helpful. We computed the projective span of these wall manifolds, so I want to tell you what those are. We have two integers, m and n, bigger than or equal to 0. The Dold manifold, Pmn, is a quotient of this product space here. We have an n-dimensional sphere and n-dimensional complex projective space. We're quotienting out by the antipodal action on the sphere and complex conjugation on the CPN part. And Dold actually built these to give generators of the unoriented cobordism ring. So there's a kind of cool connection to cobordism theory. If you reflect in the lax coordinate of the sphere, that's going to commute with this antipodal action, which will induce a homeomorphism of these Dold manifolds. And the wall manifold QMN is a mapping torus of this Dold manifold with respect to this reflection. So you take your Dold manifold Pmn, you cross with the integral, and then you glue the edges of the cylinder along this reflection. These guys, Wall built them to get at the two-torsion part of the oriented cobordism ring. So I don't have to really go into this, but it's kind of a cool connection. And we found that the tangent bundle of the wall manifold QMN splits into two mu n+1 plus n+1 lines. So this mu n+1 thing is the two-adic evaluation of n+1. So mu n+1 is the biggest number such that 2 to that number divides n+1. And this is really intimately related with those Radon-Hurwitz numbers that we saw in the span of spheres example. One really good thing about this result is that we now know that span and pspan can be arbitrarily different, which is something we really didn't know before. It turns out that if m and n are both even, the span of QMN is identically 1, but we know that you can split off m non-trivial line bundles as well. Another reason that me and my supervisor thought this was kind of striking is because the span of the Dold and wall manifolds is an absolute mess. People do not know really very much about that at all. So we were just really shocked that we got such a compact formula for the projective span. I don't want to go into the nitty-gritty details of the proof, but I do want to give you just an idea of how we prove this. Our proof is very constructive, and I need to go on a quick aside about Clifford algebras. I'm not an expert in Clifford algebras, and you probably know more about them than me. So if you're annoyed at my presentation of them, just I'm sorry. But K is a number bigger than or equal to 0. CK is a free associative algebra over the wheels with K generators, and these generators have two relations they have to satisfy. Each generator squares to -1, and EI times EJ has to equal minus EJ times EI. So C0, you can see that it's just the reals. You can identify C1 with the complex numbers, and there's a non-canonical isomorphism of C2 with the quaternions. I've given an example identification there. If you give yourself a monomial in these generators of the Clifford algebra, these Clifford relations say that you can reorder them so that the indexes are increasing, strictly increasing. And if you take these monomials where the indexing is strictly increasing, you actually get an additive basis for this Clifford algebra. And if you put a plus or minus sign in front of those things, you actually get a multiplicative subgroup. This is not really that important, but just for 2 slides, remember what this GK is, don't forget it. Now give yourself an inner product space with a CK model structure, which I'm calling rho. And I'm going to write A sub I for the automorphism of the vector space given by the ith generator of the Clifford algebra under this module map. And this gives rise to the so-called Clifford multiplication. So if you have a vector x in V, I'm going to write EI C dot X for the action of this generator on the vector X by this automorphism. We can build a GK invariant. This is the multiplicative subgroup. A GK invariant inner product on the vector space by this Aberdeen process. And the upshot of that is if you look at a vector on the sphere associated to V, the Clifford multiplication will stay on the sphere. So what I'm trying to just give you the flavor of is that these Clifford algebras and their modules are the perfect things for building orthogonal vector fields on spheres. So I want to just quickly show you how this set here is an orthonormal K-brane on the sphere associated with V. So the first thing we want to check is that X and the I times X are orthogonal, so we're going to look at their inner product. This is a GK invariant inner product now. So I can multiply both arguments by this EI, and EI squares to -1, so I can pull out this -1 because it's an inner product, and it's a symmetric with an inner product as well. So I can, swap the arguments. So we see that the inner product of X and EI times X is equal to minus itself. So it must be 0. And we also need to check that the elements of this set are pairwise orthogonal, and you can see how you just play the same game. It's just these Clifford relations that really encode this. So now I can try and tell you how we got the lower bound for the projective span of these wall manifolds. The Clifford algebras will come back in a second, but I have to tell you about this sort of key idea, these quasi-invariant vector fields. So now we have a smooth manifold with a G action, and we'll call a vector field on M quasi-invariant or G quasi-invariant if for every group element G and G, this diagram commutes up to sign. So if we have a point on the manifold, we can apply the group action and get a different point on the manifold, and then we can apply the vector field and get some kind of tangent vector. Or we can take a point on the manifold, apply the vector field to get some tangent vector, and then apply the differential of the group action to get some different tangent vector. So I'm saying this vector field is quasi-invariant if the tangent vectors you get at the end are either pointing in the same direction, they're the same vector, or they could be pointing in opposite directions. The point of this is if you have a finite group acting freely on the manifolds, and you look at the quotient of n mod g, then the tangent bundle can be described as a quotient bundle. So it's not too hard to see that these quasi-invariant vector fields on M will become line fields on the quotient. This is a bit of a long definition, so I think we should just do a quick example so that it's not too confusing. I don't have my iPad with me, so I just quickly made this in Microsoft Paint. I know it looks horrifying, but it's gonna do the job, I think. So rho here is a reflection in one coordinate of a circle. It really doesn't matter which one. And what I want to do is view the Klein buffer as a mapping torus of the circle with respect to this reflection. So we have a cylinder here. I want to show you that there's a quasi-invariant vector field on this cylinder that will descend to a line field on the Klein buffer. So there's this vertical orange lines. That's just a vector field on the cylinder, which is going to descend to a nice vector field on the Klein buffer. So nothing's going on there. It's this blue one. So if you look at this horizontal blue vector field and look at the top boundary circle of this cylinder, let's just make things easy and say we're reflecting in that gray line. And let's look at a point on that axis of rotation. So if you see what I mean, like this point is going to move when we apply rho, it's just going to be fixed, just for maximum ease. Let's say that the tangent vector assigned to that point by the blue vector field is pointing to your right. If you differentiate this reflection, basically, then it will flip the tangent vector the other way. And this is going to cause problems when we glue to get the Klein voxel, because we have a point which has assigned to it two tangent vectors that are different. They have the same magnitude, but they're pointing in opposite directions. So it won't be a well-defined vector field anymore, but it will be a perfectly good lock field. So this is this quasi-invariant thing. So what we do to get a lower bound is we notice that this wall manifolds can be written as this kind of iterated balanced product here. And that allows us to write it as some product space modulo C2 cross V2 action. So what we do basically is just we search for quasi-invariant vector fields on this product of the M sphere cross CPN across this circle. And we are able to do that using Clifford algebras, essentially because CPN is related to the 2n+1 dimensional sphere, you know. So it's a bit, I'm kind of not talking about the details, but something kind of weird comes up. So we use a complex Clifford algebra, and we use the complex spinor representation of it, if you know what that is. And we put on it, on this representation, something that we're calling a quasi-real structure. And just for people who know or care about this, if you've got a complex representation, what we're calling a quasi-real structure is an R linear and C antilinear self-map of the vector space, which squares to the identity and commutes up to sign with the module structure. And my question to the representation theorists is, have you ever seen anything like this before? And do you think it could be of independent interest outside of this very specific context? I would really love to hear your thoughts about that if you have any. But I just wanted to give you a flavor of what we did. We have, you can read our paper. It's like half-page long of horrifying formulas for the vector fields. But this is how we constructed them. And the upper bound, I'm not really going to talk about because it's very, very simple. It's just kind of basic bundle theory, and we appeal to a classical computation of the stable span of CPN. But the lower bound is the hard part. For the rest of the time that I have, I want to tell you about some related work. So far told you what projective span is. I have also told you about this new computation of the projective span of wall manifolds. Fairly recently, my supervisor in Dermot Crowley revisited the proof of the Poincare-Hopf theorem for line fields. So we all know that a smooth manifold admits a non-vanishing vector field if and only if the Euler characteristic vanishes. But it turns out that the same statement holds for line fields. So you have a line field without singularities on a manifold if and only if the Euler characteristic vanishes. So kind of the next step was to find necessary and sufficient conditions for projective span to be at least 2 or 3. I spent like the first half of my PhD trying to prove this in the real case for real manifolds, and I found out that this is already known. This year, 1987, I think on Wednesday, I think Karen was saying that 1987 is exact year with ancient times. So, oh dear. But the good thing was I always spent a lot of time doing something that had already been done. I did learn all this like super high tech, more possible obstruction theory stuff. And I and Nicola Sadovec have recently, it's not typed up yet. Well, some of it's typed up. We've solved the problem in the complex case. And so I just want to tell you a little bit what that means. So now M is a smooth 2M dimensional manifold with an almost complex structure. And if you don't know about this, it doesn't matter. But this just means that the tangent bundle of manifolds is isomorphic to the underlying real bundle of some complex vector bundle. So this is like an example result that we have, say M is odd, and give yourself a complex two-plane bundle over M. Then this two-plane bundle will split off the tangent bundle if and only if these virtual Chern classes vanish. It's easy to compute these virtual Chern classes in terms of the Chern classes of the vector bundles on the inside. And the upshot in this talk is that the direct sum of two complex line bundles is in particular complex two-plane bundle, so you can extract information about the complex projective span from these kind of results. And what's quite nice about this sort of thing is it's very specific. This doesn't just tell you, oh, there's, you know, two line bundles on your manifold. It tells you, well, if you know all complex line bundles over your manifold, you can check which combinations of them will split off or won't split off the tangent bundle. So you can get quite a lot of information about these. I also just wanted to mention that you can state this stuff like really, really generally. You can instead, it doesn't have to be the tangent bundle of the manifold. It can be like a cat CN bundle over a formal point array space. And if you say it like that, there's some indeterminacy issues. So the statements are a lot more technical. So I kind of cleaned it up here by just restricting to the manifold case. But if you're interested, the even case doesn't turn out quite as nice. There are, even in the manifold case, still some indeterminacy problems. So we don't know anything unless the top cohomology is in the image of cupping with some characteristic classes. If you have that situation, then the penultimate Chern class is the total obstruction to splitting off your complex two-plane bundle. So yeah, we have a lot of various results. We have some preliminary results that we haven't typed up yet for the complex three-plane case. And the reason we haven't typed them up is not because the details need checking or something. It's just there's so many cases. It depends on the value of n, mod 3 and mod 8. So however many cases that is, it's really a lot of calculations. But I've drawn you a classical tower because I really love drawing them. It's basically my favorite pastime. But this is the sort of thing that, you know, we are looking at. You have to compute these k invariants, and you have to do tons of horrifying spectral sequence calculations with wacko coefficients, and there's extension problems, and you have to try and compute the obstruction sets, which means you have to compute the image of certain higher order cohomology operations. It's really a fun thing to do. And finally, just in the last few minutes, I'm going to tell you about another project, which I'm also extremely excited about. This is much closer to being like fully finished. I would have talked about it. This whole talk, I would have talked about this if it was finished, but it's not quite done. It's a hard fact that not every manifold is smooth. So you can ask, you know, is there some notion of a vector field on a topological or piecewise linear manifold? And the short answer to that is yes. Unfortunately, the concept of linear independence does not make sense in this context. But there is still somehow a notion of a cat K field on a cat manifold, which properly generalizes the notion of a smooth, like K field. And cat here means either the smooth, topological, or piecewise linear category. And we have 98.75% of a proof of this result here. So M is a closed, connected, oriented cat manifold whose dimension is 0 or 4. And we're just dealing with high-dimensional manifolds here. Then you have a cat 2 fields, if and only if the Wheeler characteristic vanishes and the signature vanishes not 4. This result is well known in the smooth case. It's a classical result in the smooth case. The problem is that all of the proofs rely on this Hirzebruch signature theorem, which is really a smooth thing. You can't have one of those for topological piecewise linear manifolds. And many of the proofs also use a Tia-Singer index theorem for elliptic operators, which at least definitely doesn't work for piecewise manifolds, at least at the moment. So, yeah, I mean, what I wanted to say about this is I feel very close to this problem somehow, because I've spent many hours reading these old papers from the 60s and early 70s of Emery Thomas. And I have this like irrational feeling that I've sort of known him somehow, you know, and he tried to get a purely obstruction theoretic proof of this result in the smooth case in 1972, and he couldn't do it. He managed it when M was additionally seen to be symplectic. And I just have this sort of nice feeling that I can kind of take this project of his and sort of finish it for him somehow. So we have almost all of a purely obstruction theoretic proof. There's just this one thing that just needs fixing. I don't think it's going to be like the TBC of the whole project, which is why I'm confident to tell you about it. And then kind of the hard part is we sort of have to circumnavigate the mysterious cohomology of B top and BPL. And you can kind of carefully link the argument to these other categories. But they should be on the archive, I'm hoping really soon, so I wanted to take the opportunity to advertise it. Thank you so much for listening.
Thank you very much. Questions?
In these cases where you know that span or projection span, can you hope to get any kind of like uniqueness statement of like how many line fields realize this maximum or anything like that?
Right. I don't know. I think so. I mean, line fields are classified by the first topology of the manifold. So if you know all the degree 1 cohomology classes, then you could probably say something about how many different decompositions there are or something. Yeah, that's probably interesting.
Tell us about the lower bound. Get the upper bound for characteristic classing here.
Yeah, we didn't even need characteristic classes. There is if you have a smooth fiber bundle, say the total space is B, the base space is B, and then the fiber is F. It turns out that the projective span of the total space is bounded above by the stable projective span of the fiber plus the dimension of the base. So these wall manifolds fit into a nice fiber bundle, and you can kind of get a bound on the wall manifolds from this kind of bundle theory statement. So it's actually very simple, the upper bound.
Simply with abstraction theoretic maths with this result, I'm wondering, can you produce characteristic classes that obstruct higher lower bounds, for example, with span with bigger and free? Does it relate to vanishing of some other obstruction theoretic class that we may have often not have?
Right. Sorry, can you say this again? I think
well, when you use abstraction theory, I was wondering if this produces additional characteristic classes that will manage to increase the lower bound from 2 to 3.
right. Okay. Well, this is also something I'm interested. We have a proof that doesn't really work fully for, say, a cat3 field. And classically, what you need is the Euler characteristic to vanish and the signature to vanish mod 8. So, but I think maybe what you're saying, sorry if I'm misunderstanding the question, but there might be in this weird situation some kind of exotic characteristic classes. Yeah, and I think there probably are. There are some cache equality classes that we know about. But they're really weird because they don't satisfy the same axioms as the regular equality classes. So I think most of them hold back, you know, along the inclusion of SON to SKN or whatever to the regular equality classes. But yeah, I think you're right. There's like weird characteristic classes going on. I don't really understand that.
But there is.
Any more questions? If not, then let's have a speaker again.
Yeah, and then it's okay.
Thank you for that. Sorry.
I graduated, so keep my. For now, it still works. But it's also kind of help that. Oh, any of my friends, you know, another to another. Yeah, very hard to find. Yeah.
I'm really glad you
I
said that.
mean, my best friend, now I can't write it. It's not on social media. You know, that's.
Thank you.
I'm gonna probably. That's pretty rough. But I would love to. I am.
Yeah.
Yeah. Maybe we can do some more.
Maybe not. Yeah, a lot of friends. Back this year, like, you could put our presentation. I don't know. Maybe not clear for
First of all, thinking why this kind is so special.
Yeah.
I mean, you get the lines out of it in the level. Example of.
Yeah, but why? Yeah.
It's a good starting point. Yes.
Yeah, but it's not necessarily necessary.
Yeah, I mean, you know, it's still wonder why.
Yeah, I think that's really valuable. Yeah.
But again, really nice stuff. Really, I'm looking forward.
Thank you, I'm glad to. Everything is just so like classical, you know. It's so we're talking like 1957.
Doesn't matter. It's really down to earth. And, I think this is something good. Yeah. I mean, I'm a geometer and I find it really hard to get into this aspect machinery. It's something I can be.
Thank you so much.
I also will say one more thing. I'm not totally confident that I'm also on the clock. So excited for the I'm seeing this kind of.
Yeah.
But real. Okay. Maybe some special needs of that.
I never thought of that. Now that you say that. Okay. For the capital R. Like, real. Is this like a reality thing?
Yeah.
Okay.
I once mentioned that was should adapt it from the Spanish, real is royal, real complex.
That would actually be very helpful because
That would actually be
I always had just. And then apparently Jack the Knight will be like, so real. And then someone got mad at him and he's like, so I'm not allowed to say this anymore.
Say oil next.
Excellent. Thank you.
So I was wondering, you also have some lots on like a stable projective span? Yeah, that's the question.
Yeah, we don't, oh, yeah, so, well,
One.
yeah, well, because we computed their projective span, the stable projective span would be the same.
Oh, it's the same.
Yeah, it would be the same.
Oh, excellent.